Alright, so today we're going to be going over a 2019 A2141 16-inch MacBook Pro that has been liquid damaged that doesn't turn on. So with liquid damage, first step is always to be a visual inspection because chances are our problem is going to lie where the liquid went. So we're going to switch over to microscope view here and let's take a look. So just overview, it doesn't look too bad. We have some corrosion right here. This is our speaker amp circuit, but this isn't. There's corrosion here, but it's not that terrible. Some more corrosion right here. Corroded capacitor. Maybe something wrong there. I don't know. Might just be corrosion. USB-C controller area looks good. Another common area is, right here, of course, our 2v5 NAND generator, and that looks corroded, but I don't know if that's bad enough to cause too many issues, so we'll see there. But there's definitely corrosion there. And then, yeah, there's this. This looks like some probably like trackpad or keyboard, but this area is definitely heavily corroded, so that's noted. Some more corrosion here that looks superficial, minor. And this area looks clean. A little bit right there, that's nothing though. Okay. So let's plug this in and let's actually see what this does. So we let's plug in our USB-C amp meter. Not plugged in all the way, there we go. And 5 volts, 0.02 milliamps. So that's typical when we're either in DFU mode or we're not getting PP bus. So if PP bus is 12.3, then the board might be in DFU mode because liquid went everywhere, probably caused by our corroded keyboard controllers. And if PP bus is 0 volts, that could mean a short, or something's up with one of our CD3217s. And it is 0 volts. So I'm going to switch over to continuity mode and let me check and see if I have a short on PP bus. And I have 0.06 ohms, so that is a dead short to ground on PP bus. So what are our possibilities here? Well, these guys right here are probably on PP bus. Those can be it. This chip over here takes PP bus and bucks it down to 2.5 volts for our SSD regulator, so that could be it. I don't know if there is any PP bus lines here. So what I'm going to do is I'm going to inject small 1 volts into PP bus and let's see where our problem is. That one SSD 2v5 NAND chip, it's pretty common for that chip to fail in a way that it sends voltage to or PP bus to our SSD. Now that's obviously not good because that almost always results in a dead NAND, and that's obviously not what we want. So hopefully that chip failed in a way that it did not become a wire to PP bus and just became a wire to ground, because yeah, that wouldn't be good if that failed in that way. So we have a nice new BC50 tip here. I really like the BC50. These are our PP bus fuses. You could look at those. If you don't know where PP bus is, use your brain and the board view, and that will lead you to where the fuses are, or any point that you could solder. I'm just going to solder onto the fuses here because they're easy to get to. There. It doesn't have to be perfect. We're just injecting voltage. I'm going to start out 1.3 volts. That's nice low voltage. 1 to 1.5 is generally safe when you don't know if the issue is on a CPU MOSFET. I'm pulling 2.5 amps off the bat, almost 3 amps now. I'm going to use my thermal to kind of localize where the short might be, and instantly I see it's coming from the top of the board and near where we're injecting voltage is always going to get hot, but it looks like something in the very top corner of the board right here is shorted. And that is getting to be about 137 degrees. Now, it's probably going to be this cap right here, because this one looks pretty bad. It looks rusted, it looks nasty. And let's see, I'm just going to put a little alcohol here. See, I can't tell. So we know it's not our CPU now, so I can safely up my voltage. And there you have it. This guy is dead. You can even see the crack in it now. Yeah, look at that. There's a crack in that. So that's where our short is, but that doesn't mean this is the only problem our board has. So what I'm going to do now is knock this off the board. We'll replace it in a minute, but I just want to knock that off just like that. And now we're going to remove our wire and check and see if our short is gone, and it probably is going to be gone. So let's do that now. And back in ohms mode, we're going to measure in the same place. And our short is gone. It is, yep, in the kilo ohms now, so that is good. Now, before I can safely assess the board, we need to address this corrosion. So I'm just going to, like, these caps got to go, like these two right here have to go. But that's not, I'm more concerned about voltage crossing where it shouldn't be. Main area is going to be this SSD line, so I'm going to get flux, and I'm just probably going to replace this chip right here just to be on the safe side. This is an important chip right here, and if it is corroded, it can cause voltage to go over to the NAND, and it can cause power issues too, because 2v5 NAND is something that we need to boot. So I'm just going to remove this and get a replacement. I'm going to note my orientation as well. Actually, you know what? This one looked good. If the balls are good, the chances of the chip being internally damaged are low. So, yeah, let's look at the bottom of this chip, and if this chip at the bottom looks good, I may place it back. Yeah, see, that doesn't look bad. Sometimes these will look really bad, and this one does not look like it got damaged at all. So I can safely, when I see this, I can safely just clean up around it. What I'm looking for, so here and here are on the same line. So if I have corrosion between here and here and it's crossing voltage between here and here, that's not going to make a difference because it's on the same line. The chip isn't going to get damaged. Now if I had area of corrosion, now see how this is like collected right here? Now if I had a collection here and here, that's on a different line. That could damage the chip. But this is all on the same line, so that's really not going to damage the chip, and there's no need to replace that. It'll be fine after ultrasonic cleaning. So I am going to just kind of clean this up just like I did. I could just kind of clear this out. Yeah, this will be totally fine. Doesn't have to be perfect because it's going to go through the ultrasonic, but I am going to sit this. We don't have to reball it because it's going to go in the same place with the same balls, so same amount of solder is going to be distributed. That's down, so we're not going to worry about that. That's addressed. Now, our next area of concern is this. Now, a lot of this will probably be fine. It just looks really, really bad. So one thing we could do is just Q-tip and alcohol first just to kind of assess it and clean that up. But obviously, we're going to need flux and heat and probably to replace a few of these things. So corrosion has a way of making stuff look really, really terrible when it's actually not that bad. Like all these resistors, see the end caps, they're totally fine. Yeah, these chips are most likely fine as well. It just looks really bad when it's not. So we Q-tipped and alcohol it, see how it's not really coming off. Whenever that happens, it's best to switch to flux and heat. Now flux has cleaners and solvents in it that it's going to actually eat away and dissolve that corrosion, and it's also going to help restore any of those solder joints that may be bad. So I'm going to heat. Now we have flux down. It's going to kind of preheat from far away. And this flux is going to slowly dissolve and eat away at all of the stuff around the chip. That doesn't look too bad. This chip right there, that might need to be replaced, and some of these capacitors might need to be replaced, but all the rest of this is most likely going to be fine after ultrasonic cleaning. So there's that. And then over here, I'm going to do the same thing. This does not look terrible. So hang on a second, the board is still hot. Let it cool for a second. Alright, our board is sufficiently cooled now. I'm going to plug this in and actually see what it does. If it turns on, then great. I just need to replace some of the corroded parts, and then we'll get this into ultrasonic cleaning. Might have to replace some of those keyboard controllers. May not. I don't know yet. It's all going to come down to what its symptoms are. So on the amp meter, we're pulling 20 volts and 60. This is booting. Yeah, this is actually booting. So these are power hungry devices. Our GPU and CPU are getting warm. Now if I have 0.6 volts on vCore, that means this board is working. So I'm going to switch back over here. Here we go. vCore, 0.681 volts, and when these are at 0.6 volts or 0.7, that means they are posting. So the main area of concern here is going to be these caps on the corner here. Now, 10 microfarad capacitors are very prone to failure. I don't know why, but they are very prone to failure, and this one at the top was a 10 microfarad. I'm not going to replace it with another 10 because it may fail again. I'm going to use a 22 because on all the A1990s and all similar machines, random short on PP bus, 10 microfarad capacitor. So using a higher rated capacitor, higher capacitance and higher voltage in a decoupling application is not going to make a difference. It's not going to matter. If we're doing like audio, some stuff in audio has to be exact, but this does not have to be exact. So we're actually kind of making it better, less prone to failure. So I'll go with a 22 microfarad. I could steal this off of this A1990 board. Let me look up the voltage. Let me just double check that my voltage rating is going to be sufficient, and it's probably going to be 25. Yep, we're rated for 25, so we're good to go. And I could also replace these other two with 20. These other ones right here are for 2V5 NAND, so not on PP bus. So those are 20 microfarads, the other two. So those ones I could either use. These 22s are a little bit big, so I'm probably not going to use a 22 for those, but I'm going to use my iron to take these off because it's really close to the NAND and I don't want to damage the NAND. So yeah, iron is going to be best bet on these guys. Just like that. There's one. And there's two. Now let me find a compatible replacement for these. Alright, we're going to take these capacitors. We're going to go with 20 microfarad off of a A1990. Again, the industry has changed on how you get donor boards now, and there's really no supply chain like there used to be for donor parts anymore, unfortunately. So we have a few 20 microfarad capacitors on our PP1V8 SSD line. On this A1990, let me just triple check because I do not want to put a wrong capacitor on a board. And yep, these are all 20 microfarad. So I am going to pull these off one by one. We only need two. One here. Come on, melt. Come on. There's one. I really want to be quick on the heat in this area because the NAND. Especially on this one here. There, it's down. That's all we need. I could touch that up with my iron. Flux, because that joint is ugly. And now we should be good to test this and see if it boots. Just making sure I didn't miss any liquid. But it looks good. Now, here's the real question, are these keyboard controllers going to be dead? Yeah, I'm going to reevaluate how this area looks after ultrasonic, because I have a feeling it's not going to look like this capacitor. It doesn't look that bad. It's just superficial. So after ultrasonic, I'll just do a quick test here, but after ultrasonic, I'll either decide if these controllers are going to go or stay, because the corrosion here, it's mostly superficial. There's no burned pads or anything, and that's why I think it'll be alright. So this is too caked on for me to get off with Q-tip and alcohol. So definitely an ultrasonic bath is in order. These pads are no stuff that fell off. Yeah, right here. Right where my Q-tip is, there's two little pads there. Look like there's something missing, but those were no stuff. Right here is not bad. That should clean up nicely in ultrasonic as well. And yeah, let's see if this, wait, this one, I remember this one, BGA IC was pretty corroded right here. And this is probably something important. So this I'm going to get flux and heat. The chip itself is probably fine. Now we'll let it cool, throw it back in the enclosure, and see if it actually boots into an operating system. Alright, so I have our system board just set back in the enclosure. I'm going to plug in my USB-C. I have most everything plugged in. I'm really kind of concerned about keyboard function because those the corrosion on the controllers. So I do want to just test to see if we have a few keys working and our caps lock key works. So that's all I'm going to test there. We have fan spin. Hopefully we post. Let's listen for a chime. There we go. That is a chime, and that is an Apple logo. So let's just wait for this to boot into the operating system. All right, and it looks like we are booted into the OS. Caps lock key works, so there is some brain there on the keyboard. And our keyboard is working. I don't want to show you the customer's name, so I'm not going to show you the screen. But our keyboard is indeed functional. So this should be good to go. It also recognizes that caps lock is turned on in the OS. So yeah, this should be fixed. Ultrasonic cleaning. Reassess the areas of damage after ultrasonic, because sometimes components could, kind of get a little bit icky after ultrasonic. But this should be good to go. So thank you for watching.